Welcome to the deep dive. Today we're focusing on a really interesting new framework for training large language models. It's called Quantization-enhanced reinforcement learning, or QRL.
That's right.
We've got the source material right here, and our mission is to understand how QRL aims to make LLMs better, more efficient at complex stuff like reasoning, moving beyond just, simple recall.
And this is super important because, well, it gets to the heart of what's limiting current models. If we want LLMs to actually reason, really think through new problems, not just repeat answers learned during, say, supervised fine-tuning, they need reinforcement learning.
Okay.
But RL is notoriously resource hungry. It demands huge amounts of GPU memory, and the training, the rollouts, take a very long time. So QRL is being presented here as essentially the way to break through that resource wall.
Okay, let's unpack that resource challenge a bit more. When you talk about RL for these LLMs, it's not just running one model, is it?
No, definitely not. Often you need several running at the same time. You've got your main policy model, maybe a reference model, sometimes others too. Right. But the real performance killer, according to this research, is what they call the rollout phase.
And why is that specific part so expensive for LLM RL?
Well, think about complex reasoning. It requires the model to generate really long chains of thought, long sequences of tokens, and it has to evaluate them, often repeatedly.
Okay.
These rollouts mean tons of forward passes through the model, trying out actions, getting rewards, and all of that needs to be fast. But the existing methods, well, they haven't quite cracked the speed problem.
We know about techniques like LoRA, low-rank adaptation. That helps with the number of parameters you have to train, right? Saves memory for gradients.
It does, yeah. LoRA is great for cutting down the training memory footprint, but it doesn't really speed up the inference itself, the forward pass needed during those rollouts.
Yeah.
So the core issue, the slow rollout speed, that remains.
And then there was QLoRA. That tried using quantization, this normal float 4-bit format, NF4.
That's right. The idea behind QLoRA was sensible use quantization to drastically shrink the model weights in memory. But the way NF4 works caused a different problem for speed.
Ah, this is the hardware compatibility issue.
That's the one. NF4 is very compact for storage, great for that. But GPUs can't directly compute with NF4 weights. They have to be mathematically unpacked first. Yeah, using lookup tables and other steps. It's computationally quite involved, and it turns out pretty slow. The sources show this unpacking overhead actually made QLoRA slower for rollouts, like 1.5 to 2 times slower than just using regular LoRA.
Wow, okay, so slower.
Yeah. So the researchers realized, okay, we need a low-bit format that the hardware can handle directly, something that avoids this whole unpacking bottleneck.
So if the previous attempt, QLoRA, actually slowed things down, you'd think maybe 4-bit quantization is just not the way to go for RL speed?
You might think that.
But the research then takes this really surprising turn, doesn't it? It argues that quantization noise, the very thing people usually try hard to get rid of, is actually good for reinforcement learning.
This is really the core finding, the central insight. In supervised fine-tuning, noise is bad. It messes with accuracy, makes the model less faithful to the training data.
Right. You want precision there.
Exactly. But RL is all about exploration. And in that context, noise turns out to be an advantage. The sources explain why. Quantization noise inherently increases the model's policy entropy.
Policy entropy. How does making the policy sort of noisier help performance?
Well, think of policy entropy as measuring how random or maybe uncertain the model is when choosing its next word or action. Higher entropy means it's not just laser focused on one single best option.
Okay.
It assigns decent probabilities to a wider range of possibilities. And this effect is actually quite similar to techniques like parameter noise that are already used in traditional RL, specifically to boost exploration.
So the uncertainty from quantization stops the model from just getting stuck doing the first thing that seems okay. It helps it look around more.
That's the idea. It encourages the model to explore more broadly, discover potentially better, higher reward strategies it might have otherwise missed, less getting stuck in those local optimists.
Okay, so the noise isn't a bug, it's a feature. For RL, at least.
For RL, yes. And the QeRL framework is built around this. They specifically choose the NVFP4 quantization format. This is key because NVFP4 is a floating point format that modern hardware, like NVIDIA's H100 GPUs, can process natively and very quickly.
Ah, native support.
Right. So you get the benefit of that helpful exploration noise plus the hardware acceleration. And they combine this with LoRa for the memory savings on the trainable parts. Best of both worlds, essentially.
Okay, let's dive a bit deeper into how QRL actually works. You mentioned two key things, the hardware-accelerated quantization and then managing this exploration noise. How do they get the speed?
So the speed mainly comes from using those NVFP4 weights. QeRL uses something called a Marlin-based kernel. It's basically a highly optimized routine for the matrix multiplications that happen constantly during rollouts and pre-filling.
Okay.
Because NVFP4 is native, there's no runtime decompression needed, unlike QLoRA. This just lets the hardware fly through those calculations much, much faster, hitting the main bottlenecks head-on.
And then there's the noise management. You called it Adaptive Quantization Noise, AQN. You can't just have the same amount of noise all the time, can you? You need to explore, then focus.
Absolutely. AQN is about taking that inherent quantization noise, which is normally just static, and making it controllable, dynamic. They inject a sample's noise vector during the forward pass, but crucially, the amount of this injected noise needs to change during training.
Why change it?
Well, if you have too much noise later on, when the model should be refining its strategy, it'll never quite converge, right? It'll stay too random. You need high noise for exploration early, low noise for exploitation later.
So how do they manage that transition from, exploring widely to zeroing in?
They use what they call an AQN scheduler. It's basically an exponential decay schedule for the noise scale, which they call sigma. Think of it like training wheels.
Okay, I like that.
You start with the noise level quite high, say sigma textoric. It's maximum randomness, encouraging the model to try lots of different things, explore the whole space.
Wide training wheels.
Exactly. Then, as training progresses and the model starts figuring things out, the scheduler gradually reduces the noise scale down to a much lower level, maybe sigma 5 textiller. That tightens the training wheels, allowing for fine-tuning and exploiting the good strategies it found.
That makes sense. But adding this dynamic noise, doesn't that add complexity, maybe more memory usage, kind of defeating the purpose of quantization?
That's a really good point, and they had a clever solution for it, something they call the noise merging trick.
Noise merging trick.
Yeah, instead of creating a whole new separate chunk of memory to store this random noise vector, Z-lay standard noise for every layer, which would add overhead, they found a way to merge it.
Merge it where?
They merge it directly into the memory already used by the layer normalization parameters, things like RMS norm.
Ah, so they reuse existing memory slots.
That's it. It's computationally neat. They sneak the noise in there, avoid adding extra parameters, keep the memory footprint low, and critically, it stays fully compatible with those fast NVFP4 BF16 compute kernels.
Very efficient.
It's quite elegant, really. Gets you the adaptive exploration without sacrificing the speed and memory goals.
Okay, so we've got the how. Now, the results. What did the experiments actually show? Did QeRL deliver on speed and accuracy compared to, say, regular LoRa or that slower QLoRA?
The results reported are pretty impressive, showing gains on both fronts. For efficiency, QeRL was over 1.5 times faster in that critical rollout phase compared to standard LoRa.
Over 1.5x.
And for the really big models, the 14 billion and 32 billion parameter ones, that speedup was actually over 2x. End-to-end across the whole RL training process, it meant speedups of about 1.2x to 1.5x.
That's significant time saving. And what about memory? That seems like a huge potential win here.
Oh, absolutely huge.
Yeah.
QeRL shrunk the total model size down to only about 25% to 30% of what the 16-bit versions needed.
Wow, a quarter the size.
Yeah, and this is what really changes things in terms of accessibility. The paper mentions this allowed them to train a 32 billion parameter LLM, which is a serious model, using reinforcement learning on just a single H100 GPU with 80 gigabit of memory.
A single GPU for a 32 BRL run? That makes it feasible for way more labs, doesn't it?
It really does. It dramatically lowers the bar for doing this kind of advanced research.
But the million-dollar question, did they sacrifice performance? Did the models actually learn as well?
That's the other key part. Not only did they not sacrifice performance, they actually saw faster reward growth during training and achieved higher final accuracy compared to both standard 16-bit LoRa and the slower QLoRA.
Higher accuracy, too.
Yes. They give specific numbers, like the 7 billion parameter QeRL model hitting 90.8% on the GSM-8K math benchmark and 77.4% on math 500. According to them, This performance basically matches full parameter fine-tuning, so no real loss in capability despite the compression and speed.
And this held up across different model sizes.
It did. They tested 3B, 7B, 14B, and 32B models, and QeRL consistently outperformed vanilla LoRa on these mathematical reasoning tasks.
Now, you mentioned something earlier about stability, especially with higher learning rates. That sounded quite interesting.
Yes, that was another really striking finding. The controlled noise from NVFP4 and QeRL seems to make the whole training process more robust. They found QeRL could handle higher learning rates, like 3E5.
And that's considered aggressive.
For 16-bit LoRa training, yes. At that rate, the standard LoRa model often just collapsed. The training would fail catastrophically. But QeRL, using the same high learning rate, remained stable and actually learned almost twice as fast in terms of reward growth.
So the noise acts like a stabilizer, preventing those training blowups.
It seems to. That stability under pressure is a massive practical benefit for anyone actually trying to train these models. Fewer failed runs, potentially faster convergence, even with aggressive settings.
Okay, so let's try to wrap this up. The main takeaway for you, listening, seems to be that QeRL isn't just using quantization as a necessary evil for saving memory. It's fundamentally changing its role.
That's a good way to put it.
It transforms quantization from something you tolerate, maybe expecting a performance hit, into an active part of the solution that actually boosts speed, stability, and the model's ability to learn complex tasks through RL.
And I think the really provocative point, maybe the thing to chew on, comes from that stability finding. The fact that QeRL thrives with high learning rates where traditional methods like 16-bit LoRa just fall apart, it really highlights this unexpected power of controllable noise.
Right, noise is a tool, not just an artifact.
Exactly. It makes you wonder, if we start thinking about quantization not just for compression, but as this lever for managing exploration and ensuring stability, how might that change how we approach training all sorts of models, especially when resources are tight? It could really shift the landscape for efficient AI development.